Okay, guys, good morning. Any questions about the syllabus? Any questions at all about the syllabus? Good to go? Everybody know the magic number that I told you about in the syllabus? Good to go? I mentioned using note cards as a good way to learn material, particularly like lab reactions. There's lots of lab reactions organic too. Making note cards for studying, just making them out is useful, and then you can have them for studying. Something on the front, like a lab reaction with no product given, and then on the back the answer, maybe some other details about the reaction, mechanisms, stereochemistry, whatnot. Okay, very useful. Anybody need any note cards? Some here? Did you catch?
Yes, sir.
Okay, in lab we'll be checking in upstairs, okay? Check-in instructions are in your lab manual, okay? Everything is there. After check-in, we'll have safety information, etc. Then we'll go downstairs to a classroom, hopefully one is open, more on that side. First floor, and we will have some lecture. During lecture, we will introduce NMR a little bit. Just make sure you're know where everything is at. Videos, okay. See if there's any questions at that point on NMR. We will look at nomenclature of alcohols and ethers, which is by video. See if there's any questions on that. And we'll do a few miscellaneous things about the lab, some discussion, kind of make sure we're set with everything. Okay. Today we're moving on. Any questions before we get started? Okay, reactions of alcohols. Reacting with HX to make alkyl halides. Here are a couple of examples. Here are a couple of reactions. We can substitute this OH for an iodine. We're using this here. We have H plus, we have I minus, right? That's what we need. H plus, make this better leaving group. I'm not going to protonate. Okay, we can get to this point. Can I just do that instead of showing the protonation step and having to redraw the entire molecule? On a test, you would have to show that step. Okay, we can protonate that. We have a strong acid. What's the next step? What's the mechanism here?
SN2.
We have I minus, that's supplied by the potassium iodide. Mechanism?
SN2.
SN2. These electrons come in here and kick off the leaving group. And we have arrows, backside attack. How do you know it's SN2?
Because of the inversion of the iodine.
Because the product is inverted. Okay, it must have been SN2. SN2 comes with inversion, just like Big Mac comes with fries. Okay, there you go. There's your mechanism. Again, I didn't show the protonation step. Right? Okay. Down here, same starting material. Difference is sodium chloride is a potassium iodide. By the way, the sodium potassium really doesn't matter. It's the halide. Mechanism here.
SN1.
What's the first step of the mechanism?
Protonate.
Protonate the OH. Okay, I've already protonated it here. We can start here. What's the next step?
Water leaves.
We would
Water leaves. Okay, I'm going to just reprotonate it. Okay, at this point, water leaves, and that's going to give carbocation. That's a saturated ring. Okay, sometimes say S, saturated. It's not a benzene ring. It's not aromatic. Okay. LG leaves, ionization. Already had an ion, now we have a carbocation. What's next? Look at this product. How does the halide get on that other carbon?
hydrogen shift.
Must be a hydride shift, okay? We have an H here. These electrons break free and move over here. And we now have cation here. One H here. There's now two H's there. That's why it's neutral. Okay, why would it rearrange? This is a secondary carbocation, this is a
Tertiary.
tertiary. Yes, that's my six-membered ring, okay? I can't always. Final step,
Yeah.
Cl minus then adds to the carbocation, and we can get product. And this is what type of mechanism?
SN1.
SN1 with a carbocation rearrangement. And of course, it's the initial is the activation of the leaving group by protonation with the strong acid. Okay, why two different outcomes? It's the same starting material. Obviously, it's the difference between I and Cl minus. Why the different outcome and mechanisms here?
Because of the product. Because of the product that was
Because what?
because the product that was already shown.
Well, I'm giving you products, yes, but why did the top reaction go by SN2, and why does the bottom reaction go by SN1? It's the same substrate. There's no difference in stereokindreds.
Iodine is a stronger nucleophile.
Iodine is a stronger nucleophile. Yes. Okay. This thing is protonated, and before it ionizes, iodine is strong enough to come on in here and just kick it off and do a backside attack. On the other hand, chlorine is a weaker nucleophile, so it's not going to come in here as readily. And if it's not coming in there, well, this has time to just ionize, and then it goes by this mechanism. Yes, the key point is you have a better the nucleophile, the more prone it is to acting as a nucleophile and acting as a bully and saying, here I come, I'm kicking you off, I'm not waiting. Yes, better nucleophile. Make sense? Would you have to predict these two outcomes? No. These are mechanism questions, but you can rationalize it once you see it. Okay? If I just gave you, said predict the product here, you could show this with a chlorine here, that'd be a reasonable predicted product. It's just you'd want to question, is chlorine really a good enough nucleophile for SN2? Or chloride? SN2 requires a strong nucleophile, right? Is chloride strong enough to do an SN2? Well, it's borderline. Okay, yes, it is an anion. Like we said on Monday, it's the conjugate base of a strong acid, so it can't be that strong of an anion. Okay, Lucas. Lucas is a wet chemical test for helping to distinguish what type of alcohol do I have here in my class. Primary, secondary, or tertiary? Lucas test. And our first lab next Thursday, Friday, is actually using the Lucas reagent. Okay, you should be looking at that because this Friday, we may talk about it a little bit and see if you have any questions in advance of next Friday. By the way, I mentioned Friday. How's your day so far? Going all right? Yeah? Some of your friends still in bed? Okay, well, that's too bad because they should be up and at it. You're going to be done with organic chemistry by 9 o'clock, and now you have time to study and do something with the rest of your day. All right? I love Friday lab because it keeps your other days free. So you have Thursday lab. But what if you have a test on Friday morning? Okay? Well, you can't sometimes do much about it, you know, but that's why I particularly love Friday lab because you're in there. You don't have to worry about having a test on Saturday. What else are you going to do on a Friday afternoon? Probably ain't going to study. So do something you have to do. Leave your other time free for studying. Yeah? There's a little bit of room in Friday lab still. If anybody wants to switch from Thursday to Friday lab, let me know. Okay? But for me, I don't give you a test on Friday because I know you are in lab on Thursday. That's why our tests are usually on Monday, but this semester sometimes on Wednesday. Okay? Because I know you're dealing with lab on Friday. Either Thursday afternoon. Okay? All right. In the end, I like 8 a.m. class and I like Friday afternoon lab. All right? Because I want you guys to have more time for studying and not for something else. Assuming you want to have more time for studying and to do the best you can at your coursework. So, okay, where are we at? Lucas test. Okay, moving on. How do you make OH a better leaving group? You can protonate it, protonate any oxygen, or for that matter, nitrogen, etc. We can also have tosylates as leaving groups. Okay. Again, a lot of this is review from the end of my organic 1. Okay. Tosylate, we can convert the alcohol, the OH to the tosylate. Tosyl is the O, sulfonyl, SO2 sulfonyl. That's toluene, methylbenzene. That's toluene, it's a common solvent. Toluene sulfonyl. That's where tos comes from. Okay? And that there, the oxygen, all that is a good leaving group. Now, it's strictly OTS. I like to say OTOS, so it looks like TOS, and I say OTOS. But it's strictly supposed to be OTS. Okay, how do you make tosylates? In organic 1, I just said, okay, you can do this reaction. But let's look at this mechanism here in organic 2, tosyl chloride. Okay, this is an aromatic ring with a substituent. Regardless, we can sometimes designate an aromatic ring with sort of a, I reckon that's like the a symbol like V or something. And we have SO2 chlorine. This is just a generic for an aromatic ring, okay? I don't want to use all the ink up drawing the big aromatic ring. All right. Okay, tosyl chloride and pyridine. Pyridine is benzene with one of the CH's replaced with a nitrogen, of course, lone pair. And pyridine is a weak base, lone pair being in an sp2 orbital. Okay, basically the oxygen replaces the chlorine. All right? Under my hand, chlorine, that's tosyl chloride. Now the oxygen's bonded there. It's a substitution reaction. But it ain't SN1 or SN2. And it's our first look at a new substitution reaction. These electrons, okay, the sulfur's electrophilic. It's got the oxygen pulling, 2 oxygens pulling, chlorine pulling. Lots of partial positive on the sulfur. These electrons attack sulfur. We do not just kick off the chlorine. That's what we need to do. The chlorine is now gone from the sulfur. Instead, we move one of the pi bonds onto oxygen. Because, which is the stronger bond to sulfur? The sigma bond to chlorine or the pi bond to oxygen that I'm moving? Which one's stronger? Or I can say which one's weaker?
Sigma bond is stronger.
Sigma bond is stronger. Whenever electrons come in here, you're not going to break and kick off the sigma bond. It's stronger. Instead, you're going to move the pi bond away from the sulfur because it's weaker. If we just came in there and kicked off the chlorine, that would look like an SN2. Nucleophile N, kick off the leaving group. We're not doing SN2. We're also not doing SN1 because the first step is not leaving group leaving. It's a new mechanism. What does this arrow movement give? Oxygen, the H is still there. The oxygen is now bonded to the sulfur. We have double bond to oxygen. We have a chlorine. And then what's the other look like? Everybody knows what this arrow means? Okay, WDAM. What does arrow mean? Electrons move on to oxygen. How many lone pairs on this oxygen now?
3.
3. And that's a minus charge. Pi bond moved out onto oxygen as a lone pair. 1 lone pair left here. This is a positive charge. And we just did a nucleophilic addition. Now the next step is these electrons can come back. And already we have to take care of the proton. And along the way of the course, okay, even when we get into April, we will be dealing with the proton. Okay, it now becomes acidic, and we'll be dealing with questions.
Where did the aromatic ring go?
Very good, very good. It should still be there, yeah. Is that what the question was back there? Thank you. It's got 4 things bonded to it, now it has 5 things. This came in there, yes, okay. Okay, deal with the proton. I'm going to maybe not deal with it quite strictly yet. Let's go over here. These electrons then come back and reform pi bond, and then we're going to kick off the chlorine. And this is going to give boom, 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 oxygen bonding to sulfur. That's bonded to the aromatic ring. We had double bond oxygen. But now we reform the other double bond oxygen and the chlorine's gone. We don't magically lose an H over here. But that gives that, right? This is just turned, but now we're back to the sulfone or the sulfonyl. S2 double bond oxygen, S double bond oxygen, there's the aromatic. What do we need to do to get home? Need to remove the H. Now we did create Cl minus. If nothing else was there, Cl minus could take the H, and we would form this plus what? HCl. All right. You often don't like to form a strong acid in a reaction. All right. We probably have in the past. Pyridine is added for one reason, is to consume the HCl. It sort of acts as another reason that I'm not going to get into. But at this point, we're going to use the pyridine. All right. And this is maybe a little bit crowded on your sheet here, and I recognize that. But the pyridine can take the H, and these electrons stay behind. There. And that's our tosylate. And what's the byproduct here? Protonated pyridine, Cl minus. That would be called pyridinium hydrochloride. It's the hydrochloride salt of pyridine. Okay, pyridine is added to consume the HCl. It has another possible reason I'm not going to get into. Question.
Why don't the electrons on the negatively charged oxygen attack the positive, and then that H kicked off and goes on to the period?
Tell me again, the what?
Why doesn't the electrons on that oxygen attack the positive oxygen, and then kick off the H, and that H is taken by the...
This attacks the positive oxygen?
Yes, sir.
Okay. These electrons attack here
Yes, sir.
and do what?
Kick off the H?
Kick off the H?
Yes, sir.
What are you going to produce?
I'm just asking why wouldn't
You're going to produce H minus there.
Okay.
Because the H is taking the 2 electrons, right?
Mm-hmm.
This is H a good leaving group?
No, sir.
Okay, and you're going to produce an OO bond, which is a high energy bond, and we're not looking to make that. We know what we're looking to make. Could this theoretically happen? Yeah, you got a minus and a plus, but no, that chemistry is not going to happen. Make a high energy OO bond and this be a leaving group? Not going to be a leaving group. But it's always worth considering other possibilities. We know what we're going to get here, and the mechanism is nucleophilic addition. What are you going to call this step here? Very important. We're going to call this an elimination. We're then eliminating the chloride. And we did an addition/elimination mechanism. This is a new mechanism, and we will do this plenty down the road. And we will talk more and more about it. I'm not ready to talk much more about it. Question?
Does that ever form salts?
Can't hear you.
Does the bromine chloride ion form salts? Or is that?
Does it form a salt?
Yeah.
Well, it is a salt.
Okay.
What's a salt? Ion pair. Yeah, it's an ion pair. It's a plus and a minus. Are you saying does it precipitate as a salt?
Yes.
It depends on what solvent you're in, maybe. You probably want to add water at the end, and that salt's going to be water soluble, and it's going to end up in the waste container. If you were not adding water, it could precipitate. But it's lots of organic, because there's 5 carbons there. It depends on, but yeah, I mean, it is a salt. It all just depends on if it's soluble or not. Okay. There's your tosyl chloride. We did an additional elimination mechanism. Pyridine acted as a weak base to pick up the HCl. Here's how I could have done. I could have taken the H here. As soon as this becomes acidic, as soon as the oxygen becomes positive, the H becomes acidic. As soon as it becomes acidic, the pyridine can take it. In the future, we may actually take it sooner. That's why I said we got to deal with it. All right? I took it a little bit later. We could have taken it here. Additional elimination mechanism, tosylate. Okay, your tosylate is a good leaving group. We can do substitutions here with a nucleophile. We don't have to protonate the tosylate. All right? Some type of nucleophile with a lone pair can come in here and bam, do an SN2 kickoff the tosylate. That's the beauty of it. Now, tosylate is your most common at the introductory level. There are analogous sulfonate esters. Called a sulfonate ester. Because if that was an H under my hand, that's a sulfonic acid. You put an R group on a sulfonic acid, now we have an R group, in this case a propyl, it's called a sulfonate ester. Okay? There are other ones. If instead of an aromatic group or a toluene group, if it's just a plain methyl, it's called a mesylate, methyl sulfonyl, whatever. If it's a CF3, it's called a triflate, a trifluoromethyl sulfonate. Triflates are actually the best leaving group because that CF3 is so withdrawing. It's pulling through here and making that particularly partial plus. But why is the tosylate such a good leaving group?
It's a pseudo halide.
Because when it leaves, what does it look like? It's going to have the... Okay, you can either draw both those kind of up, or you can, it doesn't matter. When it leaves, all right, there's your leaving group for your SN2. Why is that such a good leaving group?
Resonance
It's
stabilized.
very resonance stabilized. You can draw 2 additional resonance structures. This charge actually sits on this oxygen and that oxygen, if you understand resonance. Okay? And lots of resonance stabilization makes it very stable and willing to leave without you having to protonate it. All right? All that should be mostly reviewed from Organic 1. We looked at the mechanism here and introduced the additional elimination. Use of pyridine as a weak base. We'll look at the aromaticity of pyridine during test 2. Pyridine's a good base. It has a nasty characteristic of causing testicular cancer. So be careful. Okay, reactions. Oh, by the way, these guys are very common. If under my hand was H and H, under my hand, what would that be?
H2SO4.
H2SO4, it'd be sulfuric acid. This is the diester of sulfuric acid. It's the dimethyl ester. It's called dimethyl sulfate. Because if under my hand was just like two sodiums, that is anion and sodium plus, that would be sodium sulfate. Instead of the oxygens being anions, if you bind them to methyls, you have dimethyl sulfate or diethyl sulfate. These are common alkylating reagents. And we are alkylating, correct? Because the nucleophile has no alkyl group here, but now it does because it attacked that carbon and became a carbon. It became bonded to a carbon. It became alkylated. But these things down here will also alkylate nucleophiles. It's the same as the tosylate. If over here was the toluene, that would be a tosylate with this being the carbon you attack. It's actually symmetrical and it's the same on both sides. You can attack either side, but you usually only attack once. And so nucleophiles come in here, attack the carbon, and kick off the oxygen. But these are very cheap. You can buy like a big old gallon for like 20 bucks. And so they're very common. They're very toxic because they will alkylate your DNA. Okay, your DNA has lots of lone pairs, all right, and you're going to end up alkylating your DNA, or in this case, methylating some nitrogen in your DNA. All right, so they're potent alkylating agents. Okay, let's do an example. Or actually, want you to do these on your own, and we'll look at them next time. Did we look at? Oh yeah, we started by looking at previous. Okay. All right. You need to be doing these problems and being prepared for next time, and we need to discuss them next time because time is limited in class. All right? And we can discuss them, but I only want to discuss them after you spend time thinking about them. Otherwise, it's not as useful. You need to have questions when the discussion time comes. Okay, next reaction. So, reaction of alcohols with thionyl-chloride, SOCO2, thionyl-chloride. That term should be in your textbook. Or PX3. It's another way to make alkyl halides instead of reacting with HX. Okay, take alcohol, react with PCl3 or thionyl chloride, we can get the alkyl chloride. PBr3 make the alkyl bromide. The SOBr2 is just not commonly used. You're only going to see that with the chlorine. Let's do this mechanism and then talk about why use this instead of maybe HCl or HBr. Okay, thionyl chloride is sulfur with double bond to one oxygen, and then chlorine and chlorine. All right? Just flow structure for thionyl chloride. Now, if under my hand was toluene, and if that was another double bond O, that would be tosyl chloride. Similarities. Okay. Mechanism. This attacks here. And what do we do here? Do we kick the chlorine off directly? No, we have a weaker pi bond. We're going to move this up. Move that away from the sulfur. And that's going to give Think of that. We just did a nucleophilic addition. Analogous to tosyl chloride mechanism? No? Okay. Now there's no base here, it's just thionyl chloride. Okay? And by the way, when we react with thionyl chloride, I'm doing this one. All right? We get this plus SO2 plus HCl. When you use thionyl chloride, not when you use PCl3. So let's make sure we understand how we get those two byproducts as well when we do our mechanism. Okay. Electrons up. Okay, what do you want to do next? Well, it may not be that intuitive because it's sort of advanced in showing the product. These electrons then come back down, and again, the proton, I hate that proton being over there, it looks acidic. We'll deal with that along the way. But we're going to kick off one of the chlorines. And what does that give? I'll move over here. We now have, okay, the double bond to oxygen reformed. We kicked off one of the chlorines, but there's one chlorine left. And we have the oxygen, and it's still protonated. All right? Is everybody there? We just did an addition. Followed by an elimination. All right? We get to this point. We're trying to get to these three products. What do you propose next?
Chlorine dioxide affects the carbon.
Very good. Very good. I was a little suspect if we're going to be able to see this, but yeah, it's ready to go. The chloride, do we have chloride?
Mhm.
Yeah, we just kicked it off. We made that plus Cl minus. Yes. These electrons then come in here, attack here. What are we kicking off? Can this oxygen leave? Why can't it leave? Why?
You guys have a positive charge and let's go back.
It's essentially protonated. It became protonated during our mechanism. We didn't protonate it with a strong acid. It just inherently became protonated through what we did. And there we go. And that gives what? Well, it gives our product. I mean, you can draw an arrow over there. I'm going to, okay, right? Chlorine's now bonded to this carbon. That's our organic product. Plus what? Right? Plus that. Everything comes from the arrow movement, right? Are we done?
No.
We made our organic product, but we didn't make SO2 and HCl like I told you is formed. How can you get that from here? All right. Well, here's another thing. All right, we're introducing a couple of things we're going to do many times this semester. Additional elimination. Here's another thing, and I'll say this a number of times. Anytime you can make a pi bond, you kick off a leaving group. That's an easy, fast thing to do. Fast step, easy to do. At this point, this thing, okay, by the way, these reactions probably we're usually going to be heating these reactions, okay? And heat can help drive this, but these electrons then move in here and kick off the chlorine. Anytime you make a pi bond, kick off a leaving group, easy to do. Regardless, what does that arrow movement give? sulfur, double bond to oxygen, double bond to the other oxygen as a result of this. There's still an H there,
Positive charge on oxygen.
and that's a positive charge. And there's lone pairs all over the place, but I'll just make that one complete since it's charged. And what do we make here?
Chloride.
Cl minus.
And that's going to go and take the H.
Now tell me how we get home.
That's going to take the H.
Now this can come take the H. These electrons stay here. And that's what you got, because SO2 is that and HCl, and you know the structure of HCl. But there you go. There's a lone pair there. Okay? Basically, this thing, which was the leaving group there, it sort of breaks apart further. Mainly because anytime you make a pi bond, whoop, and kick off a leaving group, easy to do. We'll do it lots of times. All right? There you go. Was that magic? Or can we understand all the electron flow and what's going on here mechanistically? And this reaction is so nice because both of these are gases. Okay? Assuming there's no water to sort of ionize the HCl. They're gases and they can be driven out. Okay? And you're left with a pretty clean product. All right, the PCl3, PBr3, that's just phosphorus with, 3 chlorines or 3 bromines. I'm not going to go into this too much detail, but this is probably attacking. It's probably just more like an SN2. You got to kick that off. But then the oxygen is going to become bonded to phosphorus sort of like this. And then the chlorine that got kicked off can come back in and kick off the O-phosphorus type thing. You can look at that on your own. It's probably in your textbook. All right? Now, in organic 2, there are lots of reactions. Some of them you a little bit of memorization. Okay? Note card. But then you have to know mechanism and all the details, and that's not memorization. But, this plus PBr3 on a note card with this on the back. And you just know. These reagents will convert alcohols to alkyl halides like we did with HX. But these reagents tend to work better than HX, particularly for primary alcohols. And thus secondary. Because HX doesn't do SN2 mechanisms quite that well. If your mechanism is SN1, HX works fine. Okay? These are alternatives to HX, particularly when you're doing an SN2 with a primary secondary. Okay? They're alternatives. So let's do a reaction here. Take this alcohol, Carl, PBr3 followed by KCN. This is a nice set of reagents here. Now familiar with PBr? Anybody? It's PBr3. Okay. And everybody knows KCN, right? One of my favorite bands from the 70s. Casey and the Sunshine Band. All right, so what does each set of reagents do? What is PBr3 going to do? Here we go. PBr3, what does it do? It's going to convert the alcohol to what?
An alkyl halide?
Alkyl halide, alkyl bromide, right? Stereochemistry though, anything? All right.
No, it doesn't. No, it doesn't sound strong.
This is typically SN2, all right? Mechanism we did, SN2. Could be SN1. It's typically SN2 though, All right? Typically SN2. Now that's secondary. It could be either SN1 or SN2. PBr3, that's reaction 1. PBr3 is going to convert this to that, and you should go through the mechanism there. And then cyanide, which you should have seen before, it's carbanion, good nucleophile. This comes in, backside attack, and what do we get? That product? And so stereochemistry goes back to the same as this. Why?
Because you're reinverting it.
Because we did 2 inversions. We did first inversion going to the alkyl bromide, and then we did another inversion. Yeah, okay. How do you make OH a better leaving group? Protonate it, convert it to a tosylate, or you can convert it to a bromide. Now that's not nuclear chemistry, that's a substitution reaction. So saying we converted it to a bromine is not really that strictly correct. We replaced it with a bromine. But by replacing it with a bromine, we do now have a better leaving group. And now we can come in with a strong nucleophile. So that's another way to get you a better leaving group. In any event, it's just a 2-step reaction that we need to be able to deal with. Okay? And there's one below. Why don't you do that one on your own? All right? And think about the stereochemistry. Okay. We did some substitution reactions there with alcohols. Now let's move on to Roman numeral 2, dehydration of alcohols. Common reaction. Remember the green sheet? Okay, we're going around on the green sheet. We can dehydrate an alcohol, very commonly done with strong acid, like sulfuric acid. Dehydrate to an alkene. All right. Mechanism. It's elimination, right? We're eliminating water. You know, 2 elimination mechanisms, E1 and E2. Which one is this?
E1?
Why is it E1?
Because it says so.
Because E2 requires a strong base. And obviously we don't have a strong base if we're dealing with sulfuric acid. It's the opposite of strong base, it's strong acid. So you can't do E2 with sulfuric acid. It has to be E1. Since it's E1, what's the mechanism? What do we do first? Protonate the OH. Can I just do that without having to redraw all of that? What's the next step?
Leaving group leaves.
Leaving group leaving. And that's going to give carbocation. What's next? We have 2 H's over here. Beta hydrogens. We have beta hydrogens here and here. Remember elimination chemistry? What do we have? Zaitsev and Hoffman? Yeah? Again, auto review here at the beginning. What do we have here? We have HSO4 minus. We also have H2O because this is an aqueous acid. Now, I like to always use, as you saw me in organic, 1, the conjugate base here. And we need to show full structure. We should never work with a condensed structure in a mechanism. Final step here. Is that going to act as a nucleophile? Will that act to the cation and give you what would be a substitution product? No, we said that. No. But this will act as a base, a weak base. Or you could use water. I'm not sure how some of you did it in other organic ones. But with me, I often use this. But I told you, it's actually strictly more correct to use water. But something's going to take the H. Okay? By the way, before we take the H here, what's the product going to be? Are we going to take H here or here?
That's probably that.
We take it here, we're making a more substituted alkene, Sate-Sef product. We take it here, and get this alkene. That'd be Hoffman. But that's also Sate-Sef. What's the difference here? Which one are we going to get here?
Trans.
E1 always gives thermodynamic product, most stable. Most stable of the three is the trans product. Right here, the groups are cis. Well, guess what? This has free rotation, right? Now, you don't have to usually show this in the mechanism for me, but this is going to rotate, right? I mean, don't things with free rotation rotate? And they can be like this or this? Okay? Yeah. Which is going to be favored, that rotator or this rotator? Right? Remember sin and anti? I mean, this is an equilibrium. This is going to be favored. It's more likely to be like this. And then whatever, okay, takes the H, and these electrons move in here, and we get that. But what did I reform?
H2SO4.
So H2SO4 is a catalyst in this reaction. Now again, you could use water here to take the H. If you use water, you would make H3O plus, and that's fine, and you would just have the HSO4 minus just sitting there. And that would be the end. That's actually strictly more correct, because how does H2SO4 exist in water? That's how it exists in water. Or even more ionized. It can ionize all the way to sulfate, as opposed to bisulfate. So yes, it is strictly more correct to use water here, because that's going to give you what you actually have. All right. Common reaction, dehydration of an alcohol. Secondary and tertiary OHs work best because the mechanism is E1. And it's very hard to do E1 with a primary alcohol, because it's very hard to make a primary cation. So dehydration of primary alcohols with strong acid doesn't work that way. It works best for secondary and tertiary. By the way, you can use HF. Why would you not want to use like HBr to dehydrate an alcohol?
Bromine's pretty strong.
Because your halides other than F are good nucleophiles. They right here, instead of Br taking an H, it's more prone to adding to the cation and giving you a substitution product where you're going to have a bromine instead of an OH. You want to use an acid where the conjugate base will not act as a nucleophile, and we've discussed that, right? HF, sulfuric acid, very common. There's one below for you to do. And one there. Now you can also use phosphoric acid. It's not considered a super strong acid, but it is strong enough to do strong acid chemistry. Sometimes when, down the road, this reaction is a little bit hard to kind of know what's happening. Like, just acid? I'm just protonating something? Well, if you can't sort of remember that it's a dehydration, just protonate. And then you ask yourself, okay, what can happen next? It's no nucleophile. It must just be ionization to make a permocation. And at that point, what can happen? The phosphate, again, ain't going to do anything. So the carbocation, what can happen to the carbocation? Well, don't forget, you can just beta eliminate, remove the beta hydrogen, and the cation becomes an alkene. And maybe that can get you to be able to predict the product. But in the end, there's a little bit of memorization. And a common reaction of alcohols is dehydration to an alkene using strong acid. Okay? There's another way to dehydrate an alcohol, and it's using pocylpyridine, POCl3. I call it pocyl because it reads like pocyl. Right? Pocylpyridine. It's actually like PCl3, but it has a double bond to oxygen. Now, phosphorus is below nitrogen, so typically it makes 3 bonds, but it can expand its octet, and here it's making 5 bonds. That's okay for phosphorus. And it's analogous to SOCl2 and tosyl chloride. It's got that pi bond there that we can think about. All right? And we'll pick up here, and we'll use pocylpyridine to dehydrate as an alternative way to dehydrate, particularly for primary alcohols, which don't dehydrate by an E1. All right, we're moving ahead. See some of you in lab tomorrow, 2:30 upstairs, and then be prepared for some discussion downstairs afterwards, including NMR. So what type of questions have come up thus far with NMR? Have a good day, guys.